I want to welcome you all. I'm Jim Kekelius, the head of the School of Physics and Astronomy. You may have noticed my voice. It might have been a mistake to compete in a 24-hour karaoke marathon. I'm kidding. It was only 18 hours. So anyway, but nothing would keep me away from hearing this talk today. Before we begin, I have a question. How many people here had attended the talks last summer on Astounding Astrophysics? Wow, okay, a lot of repeat customers, great. I don't know if you saw the talk by Lucy Fortson. She talked about the Citizen Science Project. She's one of the co-founders of the Zooniverse 20 years ago, having people on their computers doing characterizations and classifications of galaxies and other objects. The reason I bring this up is that today, June 30th, 2026, they have logged their 1 billionth classification. So if you would like to be part of the 2 billion, just do a search for a Zooniverse, and or Citizen Science, and it's very easy to sign up and participate. So anyway, I would like to, again, this is your U of M, and welcome you to, again, this summer is of Quirky Quantum Physics. And today's speaker is Professor Martin Greven, who is the Distinguished McKnight University Professor in the School of Physics and Astronomy. Excuse me. He got his PhD at MIT. He joined the U of M in 2009. He is the director of the Center for Quantum Materials. He actually founded it, and it was his brainchild. And it is a very well-funded DOE center with many faculty members, many students and postdocs doing research on some of the topics that we'll hear about. He's a fellow of the American Physical Society, a fellow of the American Association for Advancement of Science, and a fellow of the Neutron Scattering Society of America. So that's 1, 2, 3. That makes him a jolly good fellow. And with that, he will tell us about superconductors today. Martin, you have the floor.
Thank you very much, Jim, for this wonderful introduction. Welcome, good evening. I'm very happy to tell you about superconductors. But before I get started, I just want to make sure we're all here for the right reasons. So if you came here to learn about musical conductors and musical superconductors, I must disappoint you. That's not what I'm an expert on. But if that's the case, I would really like to encourage you to stay anyhow. And we'll talk about conductors and superconductors. There's no way to talk about superconductors without also talking about conductors. All right, so what's an electrical conductor? An electrical conductor is a metal that allows electrical charges, by that we really mean electrons, to flow through it very easily. So typical examples are copper or gold. So this is a schematic here of a little electric circuit that's driven by a battery. There's a light bulb that lights up because electrons are flowing through the circuit. And in the process, they're heating up the filament of the light bulb, and that creates light. Now, this is possible because in conductors, some of the electrons are very loosely bound to their atoms. And so then an electric voltage, which is provided, say, by a battery, when it's applied across a material like a light bulb, causes the electrons to break free and for there to be an electric current. And that current then in a good conductor flows with very little resistance. Okay? So schematically, you would indicate the current with a symbol I, the resistance with the letter R, and this wiggly line. And here's a voltage difference, a potential difference, which is characterized by a voltage that makes this all possible. And this is Ohm's law here, after Georg Simon Ohm, who basically found that the voltage equals the resistance of a conductor times the current that flows through it. Now, the electric current is just defined as the flow of charge per time, and its units are the ampere, and the unit of resistance is the ohm, with the Greek letter omega. Now, here's a little glitch. Okay. Now, the opposite of a conductor is an electrical insulator, right? And these are plastics and ceramics, for example. Now, this went too fast. So most elements of the periodic table, for example, are conductors. So everything that's here bluish, all these elements are conductors. Some elements in their natural state are insulators, and somewhere in between, they're, say, semiconductors like silicon and germanium. Depending on the conditions these elements are under, they can act like a conductor or an insulator. But again, most metals, most elements of the periodic table are metals and conductors. Some of them very good conductors, again, like copper. Okay, so this is again Ohm's law. The voltage equals the resistance times the current. There are a few other terms that we use. There is the resistivity as opposed to resistance. Basically, resistivity characterizes a particular material. Copper has a different resistivity than aluminum or gold. The resistance then is defined by what material you measure, but then also by geometrical aspects like the length of a wire or its area. So the longer the wire, naturally the larger the resistance, and the larger its area, the smaller the resistance, right? And again, resistance is also characterized by this symbol here. So conductivity is simply the inverse of resistivity. It's a specific characteristic of a material. It has a conductivity because it has a resistivity. And then depending on the size and shape of the material, the resistance will differ. Okay, so now how does this work in a wire, right? So instead of a smooth path, right, the electrons are flowing through a wire, but they don't go through a straight path. They zigzag. They bounce off the atoms that make up the wire, the crystal, and they collide a lot with the atoms and or ions in the conductor. And so that one needs to think of this movement basically of the electrons in some sort of average sense, right? Averaged over time or over the volume of a wire. And that is the so-called drift velocity. This is sort of the velocity with which, on the average, the electrons move through a wire. And it turns out that drift velocity is actually very, very slow. It's slower than a snail moves, basically, right? Which is kind of amazing. And yet wires can be very, very good conductors, because there are so many of these electrons that are moving together. But if you zoom in, what happens is pretty wild, actually, right? And so moving forward, basically, there's this really, or backward, there's a really odd fact, which is that electrical current is defined as the flow of positive charge. We know electrons have a negative charge, but electric current is actually defined as the flow of positive charge. And it's therefore the opposite to the direction of the drift velocity. And I wonder if you can guess why that's the case. It's one of those quirky things, which is simply because Ohm's ideas and so on came before the discovery of the electron, before one knew what was actually going on microscopically. So eventually it was realized, oh, there are electrons moving around, they have negative charge relative to other things that have positive charge. But one was stuck with that nomenclature. Okay, now what happens if you crank up the voltage across a wire? If you use an ever more powerful battery, I think you all know what happens, right? If you crank up the voltage, according to Ohm's law, given the material with a certain resistance, the current will increase, right? And as the current increases, eventually, Ohm's law will not work anymore. Ohm's law only works when things are relatively simple. Eventually, if you crank up the voltage, the current will increase and will generate more and more heat because the electrons bounce around and even light. And it's possible to do something like this, where you can melt a wire and start a fire. Okay, this is basically a thin copper wire hooked up across a powerful battery, and the wire cannot take it. It heats up, and it melts, and it can start a fire. Right? All right. Now, another thing to know is that the electrical resistance increases with temperature. So not surprising, perhaps, if you heat up your wire more and more, the electrons inside, bounce around more and more, and of course, eventually you melt your wire, right? So its resistance actually increases also with temperature. But what's really interesting is to ask the question: what happens in the opposite direction, in the opposite limit? What happens if you decrease temperature? What happens at absolute zero temperature? What should happen to a metal when you cool it hypothetically to absolute zero? Any guesses? Yes?
Well, the guess would be everything stops.
Everything stops, right? So that's sort of the intuitive guess. Everything stops, comes to a freezing halt. Any other suggestions? Well, let's explore that for a moment. All right? So around the year 1900, just shortly after the electron was discovered, 3 years earlier, but well before the development of quantum mechanics, okay? Physicists had two very competing theories regarding the electrical resistance at absolute zero temperature, and they both proved to be incorrect. Yeah? So there was the Drude model, after Paul Drude, who basically treated the electrons like a gas, right? And deduced that as thermal agitation ceases, electron-ion collisions, right, the charged remnants of the atoms in the material, would decrease, resulting in the electrical resistance of a metal dropping to zero, at absolute zero. Yeah? Okay. Now, someone else who's very famous, William Thomson, who was ennobled eventually and became the first Baron Kelvin after the river in Glasgow that his office was right next to, the Kelvin River. He invented the Kelvin scale. So absolute zero temperature is 0 Kelvin, or minus 460 Fahrenheit, or minus 273 centigrade, if you wish. Right? So around the same time, he argued that resistance would actually become infinite at 0 Kelvin. Why? Because conducting electrons would freeze solid and bind to their atoms, eliminating our free charge. Right? So you had these two very dramatically different ideas of what should happen at 0 temperature before quantum mechanics, right? Also, okay, so now I said both are incorrect. Well, here came Heike Kammerning-Arnes, who ran the first low temperature physics lab in Leiden in the Netherlands. So he had, in 1908, he had been the first to liquefy helium and was able to reach in his lab temperatures as low as 1.5 Kelvin. Very, very low temperature, right? So he was now able to try to answer that question. What happens as you cool a metal to zero or close to zero temperature, right? He used mercury because mercury can be purified very nicely at room temperature, and then he measured, of course, other materials. But this is an old graph. Basically, he measured the resistance. The units of resistance are ohm, right? Versus temperature, and he found that the resistance didn't go to zero gradually to its zero temperature. It didn't blow up and go to infinity, but it dropped dramatically to an immeasurably small value. So that's what happens with most metals. Not with all metals, but with most metals, as you go to low enough temperature, they become, well, I give it away, superconducting. All right? I'll come back to this here because experimentally, one can only always put an upper limit only on something like this. So he was not able to measure the resistance anymore, but clearly it dropped very, very dramatically. And it is said that he discovered superconductivity. He won the Nobel Prize in physics, mostly for his liquid helium work, but partially also for this. Now, I come back to that. But how cold is really 4.2 Kelvin, where he found the resistance of mercury to go to zero or become immeasurably small. Well, so absolute zero is 0 Kelvin, right? 4.2 Kelvin is a little bit above that. The baseline temperature of deep space, the average temperature of deep space, it's not 0. It's somewhere around 3 Kelvin. Why is that? Because there's what is called cosmic microwave background radiation, residual heat basically left after the Big Bang. So the outer space average temperature is pretty cold. It's about 3 Kelvin. So it's close to that. Yeah? Okay. Now, if you look at this, there's a lot of information on here. Okay. So let's just look at a few things. So the solar corona, the outer surface temperature of the sun is comparable to the Earth's core temperature, 6,000 Kelvin. But there's something called solar coronas where the temperature can actually become millions of degrees. It's a complicated phenomenon, but it is a very, very high temperature. So here's the Earth's core, or the surface temperature of the sun. Death Valley. I actually looked this up, okay? So this is disputed. This goes back 100 years. So the more recently record temperature in Death Valley was a little bit lower than that, so 54 Kelvin or so, 54 centigrade, okay? 330, close to 330 Kelvin. The average temperature of Neptune is about 72 Kelvin, far away from the sun. There's the coldest nebula, basically, that is known to astronomers is the Boomerang Nebula, where temperature is about 1 Kelvin. So that's quite below this average baseline temperature. And then there are some sensors and satellites that basically can operate at really low temperatures. And a bit of advertisement in my own lab, just a few hundred yards from here. We can reach temperatures as low as 50 millikelvin down here, yeah, to do physics measurements. And a bit more advertisement, so this is the apparatus that I'm referring to. We can also generate here the highest magnetic fields in Minnesota, 16 Tesla. MRI machines, for example, about 10 times more than an MRI machine, and about 300,000 times more than the Earth magnetic field that we're exposed to, right? All right, so it's possible to go to even much lower temperatures in physical experiments these days. But anyhow, so we are located in the Physics and Nanotechnology building. It's worth a visit, just not far from here if you have not been there yet. Now, this is really interesting to me. So measurements do not rule out a tiny non-zero resistance below the detection limit, right? So what do I mean? You've heard of Maxwell's equations, I'm sure, famous equations due to James Clerk Maxwell. Well, a lot of people contributed to this. And in fact, these are the equations in differential form as they are written on a plaque attached to a statue in Edinburgh, in Scotland, right? But interesting fact is that Maxwell actually needed 20 clumsy equations. He didn't know this. He didn't write these equations at all. This came later. Oliver Heaviside co-developed vector calculus, and he was able to reformulate this elegantly into these 4 equations. But they're known as Maxwell's equations, and they contain a lot of other people's contributions, of course. This is the first one. We don't need to understand these equations, but this basically just means that some charge, if there's charge somewhere in space, it essentially creates an electric field. There's a similar equation here where the right-hand side is 0. That just means there's no magnetic charge. There are no magnetic monopoles. Okay? This means here that if there's a magnetic field that changes with time, that creates an electric field, right? And that curls around the magnetic field. And if there's an electric field that changes with time, that creates a magnetic field that curls around. And then there's this guy here, which is Ampere's law. Basically, that just tells us that if there's a current that runs, it creates a magnetic field, right? So these are the 4 Maxwell's equations. And then there is something called the Lorentz force law, right? Which basically says a force on the charged particle can be because of an electric field, like an electric field that drives the electrons through a wire that is generated by a battery. Or an electric, that's called the Coulomb force, and then there can be a magnetic force that's because charged particles, electrons, for example, move in a magnetic field, right?
That
that's a cross product. So this is only non-zero if the electrons move perpendicular to the magnetic field, or at least have a component of their velocity that's perpendicular to the magnetic field. We're mostly interested in this right now. This basically, Coulomb's law helps us understand how a battery drives a current through a filament in a light bulb. Now, these equations, Maxwell's equations plus the Lorentz force law, right? They are a remarkable achievement of science. A lot of people contributed to it. And essentially what this means is there was basically unification of what was formerly known as electricity, as magnetism, and optics. Three seemingly different fields of science were all unified and can be captured with these 5 equations. It's absolutely remarkable, right? Now, why am I telling you this? Well, I'm telling you this because, let me just say, F is force here, Q is charge, and E is the electric field, right? When applied to materials, right, these equations are actually consistent with perfect conductivity. So measuring perfect conductivity or immeasurably small resistivity or resistance in a material doesn't prove that you have actually a superconductor. It just is still consistent with these equations. It's, in some sense, nothing new, right? So the real interesting thing is that about 20 years after Heike Kamerlingh-Onnes' discovery, I don't want to take away from that discovery, but I just want to say that there is a second defining property of a superconductor, which is actually the more fundamental property. And that is known as the Meissner-Ochsenfeld effect after these two gentlemen. Basically, if you have a material and you immerse it in the magnetic field and you cool it to low enough temperature so that it becomes superconducting, it actively pushes out the magnetic field from its interior. An ordinary metal doesn't do that. Maxwell's equations cannot explain that. So this is, in some sense, the more fundamental discovery. So you cool the material that's in a magnetic field, and the material sets up electric currents, basically, so to exactly shield its interior from the magnetic field. So that signifies that there was a phase transition, a phase transition into a new quantum state of matter. So this is the more fundamental, actually, discovery. Interestingly, though, it was not awarded with a Nobel Prize. Okay? All right. This is how things go sometimes. All right? Okay. By the way, feel free to ask questions anytime. And we'll also have a Q&A afterwards. All right. So now, a superconductor basically can carry persistent current. So this is the Meissner effect. You apply a magnetic field above the transition temperature, you cool the material, and it basically expels the magnetic field lines from its interior. But if you then turn off the magnetic field, right, there will be a current running in the superconductor that generates its own magnetic field to sort of mimic the magnetic field as was previously applied. And that current basically theoretically runs forever if the material is kept cold enough to be superconducting. People have done tests for several years and had no detectable decrease in the current in their tests, right? So this is a persistent current, and this is why we love superconductors, because a good superconductor can carry enormous current as long as it's cold enough, and therefore generate enormous magnetic field. And I'll come to some applications in a moment, right? So such a current is impossible in normal electric devices, since in all commonly used conductors, even copper, there's a non-zero resistance, and this resistance would rapidly dissipate. You know, energy gets lost, basically, in form of light and heat. And that's, in some sense, a waste. That's not what you want here. Here, you want a device in applications that basically generates strong magnetic fields and that you can use reliably. Oops, I'm sorry about that. Right? So this is essentially what I said. Okay, now, here is another demo. We can't do the actual demonstrations here in this room, but I now want to show you what I think is, you may have seen this before, is here you have very strong ordinary permanent magnets, And this is in there is a disk of a superconductor that's kept cold with liquid nitrogen in this case, so that it's superconducting, and then see what happens. It just hovers above the magnets. It doesn't wiggle. It doesn't fall off. Okay? It's levitating, as long as it's cold enough and superconducting. And this has to do with the fact that the permanent magnets generate a strong magnetic field, and the superconductor basically tries to expel those fields. And when it does that, basically, it sets up these currents, it generates its own magnetic field, and that constellation basically creates this enormous stability and this repulsion. And so that then is something that is being used, and I'll say more about that in a moment, to do this. This is now a track of strong magnets, and the track basically guides the superconductor. You don't need to steer it. It's sort of self-correcting. Yes?
Does the action of the superconductor pushing the ambient magnetic field out of it produce the magnetic field that we see here? Like, if you were to remove that ambient magnetic field, would it still produce this magnetic field? Or?
The superconductor responds to the external magnetic field. So you need both. You need that to get the superconductor to do its thing. And so the electric currents that are generated inside that, and the moving current creates its own magnetic field. And so it's sort of like two bar magnets with their north poles or south poles repelling each other. But in a way that's remarkably self-correcting. So you can move things around without friction. All right, application number 1, maglev trains. I had to look this up, and I double-checked. World record some years ago in Japan, almost 600 kilometers per hour. A passenger train, basically, right? And so these trains, right, they have superconducting magnets in the wagons. They need to be cooled, right? And then the tracks are made up out of permanent magnets, rare earth-containing permanent magnets. So it's not cheap to build a track like this. But it's been done, and it's being developed quite rapidly also in China. And so you need to have these superconductors in the wagon, basically, and keep them cold. But then this thing is hovering above the track, and you can push the whole train. There's no resistance. You can push it. It's amazing. Science and computing, next week's Quirky Quantum lecture will go into detail on quantum computing, so I won't say anything about that here. Okay. Particle accelerators, so facilities like the Advanced Photon Source at Argonne National Lab outside of Chicago that we use for our experiments, my group, where there are strong magnets basically guiding electrons around, and these electrons basically, since they're accelerated in a circle, they emit light, photons, X-rays, and so you can do lots of X-ray experiments there. So that uses superconducting magnets. Superconducting quantum interference devices, we have this in this strong field setup that I mentioned. We can actually measure tiny, tiny magnetic fields in quantum materials. And these squids, as they're called, are also used for geological surveying, medical neurology, to measure tiny magnetic fields. Yes?
Is there a specific material that's best for the different applications? It doesn't vary by
Yes, there is a set of materials, conventional and non-conventional, I'll come back to that are more ideal than many others. Yeah, I'll come back to that. Healthcare MRI machines, I already mentioned that. This is a photo from Mayo. Power cables and fault limiters. Of course, if you can hypothetically transport energy from place A to place B without any heat and waste it in the cables, that would be ideal. You'd save a lot of energy. And then this is the real trophy here, if you wish, fusion energy research. What does superconductivity have to do with fusion energy research? Well, fusion basically is the process of in this particular case, of fusing together hydrogen atoms to become helium, which is the process that energizes the sun. right? Our sun, our star, and other stars. And so if you want to do this in a lab, you need to create a very, very high density of hot hydrogen, or isotopes, deuterium and tritium. And so hot that the electrons are ripped out. So you essentially have just the protons and neutrons. And you need to confine that. And the only way you can do that is with very strong magnetic fields. Because of the Lorentz force that I mentioned earlier, magnetic force acting on charges, you can use strong magnetic fields to confine a really, really hot plasma. Okay? So now, this is a new recent, 5 years ago, world record, where at MIT, they managed to create a 20 Tesla, so that's more than the magnetic field we have in our lab, magnetic field, but in a huge system, the 10-ton magnet. So what weighs 10 tons here is the coils, right? So you need a large volume with a very large magnetic field. And this is done with a particular material, yttrium barium copper oxide. So this is one of those specific materials that is very desirable. So if and when, I would think, fusion becomes a reality on Earth, our energy problems are solved. With fusion, hypothetically, you can get more energy than you can dream to waste and use. Okay? All right, so superconductivity has seen many discoveries. I won't be able to delve into them. I mentioned all of them. Heike Kamerlingh-Onnes's original discovery. I'll mention a few more. All right, there are 3 more related discoveries in superfluidity, which is sort of the analogous phenomenon of a liquid to lose all its viscosity and flow without any resistance. All right. Now, in the mid-50s, these 3 scientists, John Bardeen, Leon Cooper, and Robert Schrieffer, developed what is known as BCS theory, and eventually shared the Nobel Prize in Physics for their theoretical insights and how superconductivity actually works. Right? This was a major breakthrough. It took nearly half a century to figure things out. And a few words here. Bardeen is the only person to win 2 Nobel Prizes in physics. There are a few other people who won a couple of Nobel Prizes, but no one else who has 2 in physics. The first one actually came in 56 because he co-invented the transistor. He was here at the U for 3 years as an assistant professor. He may have done his groundbreaking work here at the U had it not been for World War II. And so he got drafted and then eventually ended up at Urbana at the University of Illinois. Okay, how does superconductivity work? There's a lot on here, don't worry about that. Basically, electrons move through the atomic crystal lattice of a metal, right? And they bounce around a lot, as I said, sort of kind of zigzag motion because they bounce into the atoms and so on. There's a lot of resistance generally. But an electron has a charge, right? And it can interact with the ions of the crystal lattice here via its charge and sort of create a bit of a wiggle, basically, a wave. And which is referred to as phonons. Phonons are the quantized waves of atoms in the material. Another electron, basically, at some later time, can notice that wave and couple to it. So electrons have like charges, they repel each other. But through this interaction, the mutual interaction with phonons, the vibrations of the crystal lattice, they can actually form a pair and interact. In a way that binds electrons into pairs. These are called Cooper pairs. And the Cooper pair, basically, generation is extremely important for superconductivity. So electrons pair up into Cooper pairs, and when that happens, there are many Cooper pairs, and they all basically act in sync. And that's essentially the superconducting state. Right? So Bardeen, Cooper, and Schrieffer basically made various contributions to this understanding of how superconductivity works, and it is basically a mechanism, a whole theoretical framework, and then a particular mechanism whereby electrons get glued together into what is called a Cooper pair because of their mutual interaction with the vibrations of the crystal, right? Okay, so now it seemed to many that this problem had been settled, and the record TC was 23 Kelvin in the mid-80s. This is one of those desirable materials. This and a similar material is what is used for MRI machines, for example, many superconducting magnets, right? But then there came a really monumental discovery in '86 of a superconductor with a transition temperature much higher than this, 35 Kelvin, higher than what at the time many thought was the theoretical possible limit of 30 Kelvin. And this was made basically by Bednorz and Müller at a lab at IBM in Switzerland. They're working on this on the side. They're not supposed to be doing this. They had other directives, but that was their hobby. Okay? And this doesn't happen very often, but a little more than a year after this discovery, they already were awarded the Nobel Prize in physics. It was a huge deal, in part because of the promise that now, well, I'll tell you why. In part, basically, because their initial material said here at around 30, 35 Kelvin in the year '86, right? So this is sort of a timeline of critical temperature versus time. But then within a year, less than a year, others had found superconductors similar to that with even higher transition temperatures. And so high that, you now could get away with cooling the material with liquid nitrogen to get it to be superconducting, as opposed to liquid helium, right? Liquid helium is very expensive. Liquid hydrogen, if you buy it in bulk, is cheaper than milk. All right, so there was this huge promise that we will get all this superconducting technology, and it's actually coming into being. It's just taking much longer than initially anticipated. It's been 4 decades, right? But it's happening. Now here you see mercury, Heike Kamerlingh-Onnes. Here are some conventional superconductors that are used in wires: niobium-3 germanium, niobium-3 tin, right? There are many others on here. I just want to, again, tell you a little bit about what we do. So the most desirable of these cuprate superconductors, as they're called, have mercury in them. They're most desirable because they have the highest transition temperatures and they are structurally relatively simple. We figured out a way to grow nice large crystals of that. No one pretty much can do that still. And so that gives us an edge in our research. There are other materials like barium bismuth oxide that sits here. That's an oxide superconductor as well. There are materials like strontium ruthenate that is not on this graph. Strontium titanate, that's not on this graph. That was discovered in the early 60s to be a superconductor at very low temperatures. That might seem boring, but the killer is really that in all these oxide superconductors, we physicists still don't understand what the pairing mechanism is, what the Cooper pairing mechanism is. It's the coupling of the electrons to the phonons I mentioned earlier in conventional superconductors. But in these unconventional superconductors, it's very likely something else. It could be coupling to charge or magnetic fluctuations, okay? So even though this material here is strontium titanate, you can buy this commercially. It's used in many applications. You can buy, superconducting wires are now made. The Chinese have a big maglev project, which is going to be using high TC cuprate superconducting wires. I showed you this breakthrough 20 Tesla magnet experiment at MIT that involved one of these cuprates, right? These materials are very desirable. And engineering is pretty advanced by now. After 4 decades, I mean, it should really be, right? But physicists are limping behind. We don't quite, and we're still arguing about what the pairing mechanism is. So these are fascinating materials. And again, some of them you can just buy online. I've had high school students in my lab over the summer who were able to make these. That's the easy part. But understanding how they work, that's really fascinating. So all of these materials basically have in common that they contain cages of metal and oxygen. shown here oxygen in blue and the metals in red, right? And then these cages can be forming like a cubic grid or more like a layered structure where you have one layer here of copper oxygen sheets, another here, another here. So they have this in common, these metal oxygen structures. They're called oxide superconductors. And they tend to have very complicated looking, uncomplicated phase diagrams. You know, this is, for example, the temperature versus hole doping phase diagram of the cuprate superconductors, where here is superconductivity. There's something called a hole or holes in condensed matter physics. So a hole is simply a missing electron. Sometimes it's much easier to think about missing electrons than to think about electrons themselves. And so in this case, it's much more natural to think about holes. So this is the phase diagram, basically temperature versus hole doping of the cuprates, where TC can go up to rather high temperatures, but not room temperature. Now I should say, let me come back to this for a moment. There are some halides up here, H2S, and the new record 2019 is, I think, 250 Kelvin. So some seemingly conventional materials are superconducting close to room temperature by now. But the caveat is that you need to subject them to extremely high pressures, like a million times a million times the pressure that we're exposed to here. Okay, crushing pressure. Then you can have superconductivity at 250 Kelvin. So the idea is that if you understand how these oxide superconductors work, then hopefully you can design materials that are superconducting at room temperature or even higher, so that we don't have to cool them at all anymore to have these desirable properties. Okay, so let me skip this. This is a bit of an exaggeration. This is a review paper where these eminent scientists, they got maybe carried away a little bit, but not by that much. So the discovery of high temperature superconductivity in this oxide, lanthanum barium copper oxide, ranks among the major scientific events of the 20th century. I would have been slightly more modest and said maybe of the last half a century, because this was published 10 years ago, and there's a lot of interesting science that happened, especially during the first half of the 20th century. As I sure you know, and as I try to advertise also, the whole development of quantum mechanics, for example. Okay, but still, this is 4 decades have passed, but more than 200,000 papers have been published. Still no consensus what is the Cooper pairing mechanism in these copper oxide superconductors, all right? So how does superconductivity emerge on cooling and with doping and so on and so forth? All these materials are made out of sheets of copper and oxygen, basically. They have these metal oxygen units, but fundamentally, these copper oxide superconductors are made up out of sheets of copper and oxygen. And then what changes from one material to the next is how these sheets are stacked in the third dimension, right? There are hundreds of these materials. This is the one that I'm a big fan of, that we managed to grow nice crystals of, because it's relatively simple structurally. Okay, now, I want to just say a little bit about these copper oxide superconductors, because it's been, other than silicon and semiconductors, more recently also carbon-based materials like graphene, this is pretty much the most intensively, most widely studied class of materials, right? And so you have this phase diagram here, right? And you have Nobel laureates, very smart people who won the Nobel Prize, Bob Laffin's case, for helping to understand the fraction quantum Hall effect. Won't be able to talk about that. Phil Anderson, maybe the most important condensed matter physicist of the 20th century, who won the Nobel Prize in physics only once, but had contributed so much he probably could have earned it 3 times over. Right? So anyhow, these folks had very different, or have, in Bob's case, a very different views of how to think about this phase diagram, right? So Phil Anderson would say, well, we need to start thinking about it from zero doping. What does that mean? So if you take the original material, lanthanum barium copper oxide, you take the barium out, just lanthanum 2 copper oxide, all right? I showed you a schematic of the structure. That material sits here, okay? And it basically, lanthanum wants to give away 3 electrons to have a closed shell configuration of helium, to be stable electronically. Oxygen wants to take up 2 electrons to be stable and look like neon, okay? That leaves copper basically with the 2+ state giving away 2 electrons, effectively to the oxygens. So it has the argon electronic shell configuration, and then it has 9 out of a possible 10 electrons in d orbitals. What does that mean? So there are certain electronic orbitals that are the outermost basic electronic states of a copper ion in this material. And there are 5 of these orbitals. Each orbital can basically accommodate 2 electrons, one with spin up and one with spin down. Okay? Because of the Pauli exclusion principle, that's it for electrons. So that means that this outermost electron is lonely. It's by itself. All right? And so that also means that these coppers have a magnetic moment due to this outermost electrons. It also means that, well, you can think of this as having 9 electrons in the d orbitals, or a missing electron called a hole, right? And that's what I said earlier. We like to think about holes sometimes. So a hole is a positively charged, essentially, entity that's a missing electron. So there's a spin degree of freedom, a magnetic degree of freedom associated with this copper. Now, there's a theory that was developed that's remarkably successful called band theory. Band theory would predict that this material, lanthanum copper oxide, that sits here at 0 doping, is a good metal because it has its outermost orbital is half full with electrons. That means that electrons should be able to float around quite easily. But instead, it's an insulator. It's an insulator because it's a Mott insulator because of the strong Coulomb force, and the situation on this 2-dimensional grid plays out such that electrons much rather stay localized and just wiggle around a little bit than to move around. Okay, so these are so-called Mott insulators. They are not metals, even though they're supposed to be, right? And so then there's the magnetism on the copper, right? And so this magnetism survives if you manipulate the material. And so many think that it's magnetic fluctuations that do the Cooper pairing instead of the atomic vibrations. Maybe, right? Certainly Phil Anderson thought this is the starting point at 0 doping. And he had very exotic ideas, actually, what the mechanism is. Not magnetic fluctuations at all. I can't explain it here. All right, so blah, blah. So basically, this material is supposed to be good metal with 1 hole per copper moving around, right? But instead, the effective hole concentration is 0. Instead of 1 hole per copper that's moving around, we have 0 holes per copper moving around because it's insulator. Over here, this side of the phase diagram, band theory works. It looks like an ordinary metal over here. Okay, you can manipulate these materials to be either here or somewhere in between. And band theory works, all right? And so Bob Lovett said, well, let's start here. This is what we understand. And there's nothing really obvious that should prevent us from thinking how we go from here to here, right? So they had major clashes when Phil was still alive and couldn't agree. How do you get the holes in there? Well, you grow a crystal that is not just lanthanum copper oxide, but where some of the lanthanum is replaced with strontium or barium, as it was the case in the original discovery by Bednarz and Miller. And barium or strontium are basically like to give away only 2 electrons. Lanthanum likes to give away 3 electrons. And that means that effectively for each strontium atom that's there in place of a lanthanum atom, 1 hole is created, 1 additional hole is created in these copper oxygen planes, in addition to the one that's already there for each copper. Okay, so there are others who have other ideas about how these materials work. Chandra Varma, who actually graduated from our department here a long time ago, is a famous physicist, Subir Sachdev, who's at Harvard. They proposed that there is something called a quantum critical point, that basically means that there is some kind of hidden kind of order, electronic order, that no one has maybe discovered yet, that lurks down here, and it transitions to a disordered state at 0 temperature. And the quantum fluctuations associated with this kind of quantum critical point basically are responsible for all the strangeness of these materials. For a while, actually, I thought this is very appealing. But it's not correct. I don't think so. And Laughlin and Anderson, they're both half correct and half wrong. And I'll conclude basically by telling you we grow our own crystals and do lots of measurements here and then at various labs where we bombard them with neutron beams and X-ray beams to learn about the magnetic fields and electric fields inside the materials and how charge waves and magnetic waves, what kind of waves exist. So I'll summarize basically what I think is happening in these cuprates. And that is that there's not just one, but probably 3 elephants in the room that people have overlooked. And it's actually not so hard to understand what is missing in the picture that people had. So these materials, the theoretical physicists, they think of these materials as being made up of these sheets of copper and oxygen that are stacked. And in fact, they just consider one sheet. And they consider a sheet that's flat, where basically each atom is equivalent to the next, where you can just translate over the copper atoms or oxygen atoms, okay? But it turns out if you look very carefully with X-rays and neutrons and also deduce this indirectly, that these sheets must be rumpled. They're not flat. That means that there's a fundamental assumption that the theorists have made, which is what is called lattice translational symmetry, this periodicity. That's actually not the case. These materials are quite inhomogeneous inherently. And that opens up a new set of possibilities as to how one can understand what's going on. I told you how these materials, when they're undoped, they're supposed to be metals according to band theory, but they're not. They're not insulators. So you have one hole that's stuck on each copper. But then if you dope them with some additional holes, these holes start to move around, and eventually you get 1 plus p. If you dope p holes, you get 1 plus p holes. All the holes that formerly were localized in the copper are now moving around, right? And that's what Bob Lofton says, start on the side that's easy where the system is a metal, right? So the big question is, how do you go from the situation where the holes are localized but are supposed to move, and then you dope additional holes, and then everything moves like in an ordinary metal. So the holes that are formerly localized on the copper must be delocalized. They must start to move somehow. And the big question is, how does this happen at 0 temperature? Does it happen through a quantum critical point or in a different way? And if you allow yourself to think that these materials are inhomogeneous, you realize that these holes delocalize not collectively, all coppers at the same time, but one here, one there, right? And if you think this through, then you can also understand that as you heat these materials, the number of holes changes with temperature. So most, by far, physicists who've tackled this problem have assumed that the hole density, basically, in these materials doesn't change with temperature, but it changes with temperature, right? But in a very inhomogeneous way. Anyhow, there's another point here that basically is that you can do some experiment and realize that the way the electrons scatter around is actually fairly ordinary. But you can only come to that conclusion, as we did, if you study the most ideal materials, which this mercury-based material really is. Because then you either see things that others have seen before, and that's gratifying, you just confirm what others have seen before, or you see something different, and then you have reason to pause and to think, why is it different in this supposedly more ideal material? And that has brought us a long way. Yes?
So in this model, is pairing still the operative way of reducing resistance to the coupling?
So pairing must be going on. There's no way around that. The question is, what binds the holes, in this case, not electrons, into pairs? And in my thinking, it's sort of the charge fluctuations that have to do with how these holes ultimately delocalize away from the copper. There are some charge fluctuations, there are magnetic fluctuations, but it plays out locally on a short length scale because the system is actually inherently inhomogeneous. And so there has to be pairing. And we know there's pairing. Oh, and one more interesting thing, and then I'll close. So in an ordinary superconductor, electrons pair in a way that one electron moves here with a spin down, right? And it leaves a wake behind. It polarizes the atomic lattice. Another electron sometime later with opposite momentum and a spin up notices that wake and couples to the first electron in sort of a tiny late matter. So they form a pair of 0 total momentum and 0 angular momentum. They don't dance around each other. In these copper oxide superconductors, They're still pairs. This time they're made up out of holes, missing electrons, but they dance around each other. They have an angular momentum. That's also undisputed. Right? Okay, so there's some interesting differences to conventional superconductors. All right, so with that, let me conclude and take questions, more questions. Thank you.
Thank you very much, Martin.
With zero resistance, is the capacity for current infinite, or is there some other limiting factor that comes into play?
So there's a critical temperature above which superconductivity goes away, but there's also a critical current. So if you try to force too large a current through your wire, the superconducting quantum state also collapses. Does that answer your question? And for application purposes, you want to have critical currents as high as possible, so you can run currents through that as large as possible, so that you can generate magnetic fields that are as large as possible. And by the way, the 20 Tesla in this magnet experiment at MIT for the future fusion experiment, 20 Tesla is exactly what is needed apparently in order to tame the plasma of hydrogen, basically. So that was really an important achievement. With large currents, very large currents.
Oh, yeah, Amanda, there's someone over there. Yeah.
Hello, it works. A question of cost. You spoke of fusion being possible, and what are the costs? For instance, when we have alternate forms of energy, often there are costs to manufacture those, and do those at some point offset things like that?
Well, that's a tough one. So I'm an optimist by nature, and I think controlled fusion will become a reality. Now, whether that's going to be in 10 years or 100 years, hopefully not more than that, I can't tell you. But imagine we could basically generate all the energy we consume in this country with just a few fusion reactors. There's an enormous cost that went into the research and all of that, but ultimately, that will be nothing in terms of the cost-benefit analysis long term. So I think along the way, as these things go, there are often many serendipitous discoveries that are made that lead to something else, and you would need to factor that in, and so I think I'm in favor of supporting this kind of research based on just fundamental science considerations. But then the prospect for humanity is enormous.
Is there such a thing as a super insulator where the conductivity becomes zero?
Yes, so these Mott insulators, so the parent materials of these copper oxide superconductors are actually very, very good insulators, Mott insulators. And there are some that are even better insulators of electricity. Actually, I don't know, which material is deemed the best insulating material, but ultimately, this has to do with a number of things. If you make the atoms be further and further apart, their electronic orbitals overlap less and less, and there's less and less reason for the material to be a conductor. Then you just end up eventually with isolated atoms. Conversely, if you put something under enormous pressure and bring it closer together, you tend to get better conductivity. So there is sort of that tension, between insulating behavior and conducting behavior, just from the consideration of how close the atoms are to each other. And there are probably hypothetically some materials that could be created by pulling, atoms further apart. But anyhow, many materials are insulators. And certain ceramics are. One of the remarkable things was that these cuprates, they're not great conductors. Ceramics are generally thought of as insulators. And yet they become superconductors at record temperatures. So these materials actually are close to being insulating, and actually really good insulators.
Well, we had some questions during the talk. Excuse me. Let's thank Martin again.
Thank you.
So I just have a few announcements. Let's see. Does this work? Is this the clicker? Oh, that's the clicker. That's why it doesn't work. Okay, so what's next is next week we're talking about quantum computers. Professor Fiona Burnell, who studies these theoretically, will talk about quantum computers and the spooky action at a distance that Einstein was opposed to. But we're not afraid of ghosts. So, and she will explain quantum entanglement, the two-slit experiment, and it's be a lot of fun. Let's see, what else? Oh, this isn't going now. Great. Okay, I also ask you to join our mailing list. We're recording these, and my talk has been posted on the YouTube page. Martin's talk will be posted in a few days, and you'll get notices of when that happens. You'll also we'll send out supplemental physics information content about the subjects that we've been talking about. You'll learn about exciting physics research going on at the U. There's the QR code to get on our registration list. I also have some more books to give out. Don't bother checking underneath your chairs. We're going to do it a different way today. So I have a number of books here. Is today anybody's birthday? Is this week anyone's birthday? Okay, we got one. Okay, great. Come on down. Is this month anyone's birthday? Okay. Actually, I think I have enough books. I'm not going to go to this year. But your half birthday? Well, I got half a book for you. So, very good. Here you go. So, those people who have a birthday this month, come up. Okay, you come up after in a second. And the last thing I just want to say is I want to thank Martin and the other speakers that we're going to have in the next few weeks for volunteering their time. And we put this all together because we like to share what's going on with the public, with the community. You people support us, and we thank you for it. But we could always take some more support. So this also you can get on our webpage. So with that, I'd like to thank Professor Greven again.